Greetings, everyone. On Thursday, a couple of people said that they feel a little mushy in their head about how all those different concepts are related. So hopefully this little 5-minute video will really string them together and you'll see how each one is connected to the other one. I think this is one of the keys to understanding the whole unit. In lecture, we used polynomial division to represent the function on the left as an infinite polynomial on the right. We're going to be learning a different technique later that's a lot more powerful so that we can represent any function as an infinite polynomial, but right now this is the one we have. So we wrote that the left side equals the right side, but are they actually equal for every x value? No, we figured out that they're not. Only for x values between -1 and +1 does the left side actually equal the right side. That's called the interval of convergence for the series. It's because if you plug in an x value that's not inside the interval of convergence, the infinite polynomial on the right-hand side is not going to converge to a number. Here's what it looks like graphically. On the left-hand side there, you can see our 1 over 1 minus x. On the right-hand side in blue, you can see the infinite polynomial. And as you can see, they match each other exactly in that green region along the x-axis from -1 to +1. So there we have again the interval of convergence. Also remember we had the term radius of convergence, which is half the length of the interval. Alright, so the next question is, let's say we have some other series. You don't know how I got this, but let's pretend natural log of 1 plus x is represented by the series that you see on the right there. We want to know for what x values are those two things actually equal. And that's the same thing as asking, how do you find the interval of convergence? Well, we're going to learn some tricks for this, but all of the tricks are based on a more specific question. Not how do you find the whole interval of convergence, but how can I test a specific x value to see if it's inside of the interval of convergence? So as an example of that, let's look at x equals 1/2. So the question is, if I plug in 1/2, will my entire infinite series on the right actually converge? So we'll plug it in. As you can see here, I've plugged in for the x values in red. And so now I've got this numerical series. And again, I want to know, is it inside the interval of convergence for my series? So I want to know, does that entire numerical series actually converge? Well, that's another question. And this is what we talked about partial sums for. So if you have an infinite number of things you're adding together, and you want to know, do they converge, you got to look at adding one term at a time. That's what partial sums means. So we'll look and see what happens when we have one term, and then what happens when we have two terms, and then what happens when we have three terms. We get these sums on the right-hand side. So if I was going to add an infinite number of terms, does that sequence of partial sums actually approach a specific finite value? So this links another concept, whether or not a sequence converges. So here we have a sequence of numbers, but that sequence represents the partial sums, and we care about the partial sums because we want to see whether or not a particular value is in the interval of convergence for our original series. Okay, so let's look at those partial sums. Here I have labeled S1, S2, S3, each partial sum adding on one more term. It certainly looks like they do converge. So the first partial sum on the very right-hand side is 1/2, and then the second one, we subtract a number, and S2 is on the very left-hand side, and then S3, we add a number, so that's there in the middle. And so it seems like every time we're alternating adding and subtracting, but the magnitude of what it is that we're adding or subtracting is getting smaller. So it seems like we're bouncing back and forth, and we're converging in on a number there. Okay, well this is just our intuition. Does it actually converge? We could imagine maybe not. Maybe when you zoom in really close there, it actually just oscillates forever instead of actually getting closer and closer to a limit. So on Monday, we're going to look at some tests that you can use to answer the question of whether or not it actually converges. If your sequence passes the test, then it converges. And you can link those tests to the actual definition of convergence so that you can be sure that they're actually going to be true. Okay, let's zoom back out. Why do we care whether a sequence of numbers converges? The answer is because it tells us if the partial sums of an infinite series converge. Why do we care about that? Because that's what it means for your power series representation to converge at a specific x value. So why do we care if the power series representation converges at an x value? Because that means that the x value is in the interval of convergence for that power series. So why do we care about the interval of convergence? because that tells you where your infinite series is actually equal to your original function. And that was the original question that we were interested in. We have a function, we find an infinite series representation, and we want to know what x values are these actually equal for. So if these ideas are still mushy in your head, I would practice telling the same story yourself. Take this basic question that we want to know, what's the interval of convergence, and then go step by step. How do you figure that out? And that will take you through the convergence of an infinite series, that will take you to the partial sums, that will take you to the convergence of the sequence of partial sums, and then zoom back out again. That's how all the ideas are connected together, and that's what you need to keep in mind through this whole unit. Okay, let's zoom out further. Well, why do we want to represent a function as an infinite series at all? All this work to find where's the interval of convergence. Why do we care? So there's three kinds of answers. The first answer is polynomials, even infinite ones, are super easy to manipulate. They're very easy to integrate. They're very easy to take the derivatives of. So it can be convenient to represent other equations that might be messier as an infinite polynomial. A different kind of answer is that infinite series are sometimes the only way to express some kinds of function. So this function here is a really common function used in probability. You'll notice that it's written in the form of an integral. If we actually want to evaluate this integral, you'll find that this is one of the integrals that humankind doesn't know how to evaluate directly. So instead, you have to represent the integral as an infinite series. So that's the kind of thing that it's used for a lot as well. Finally, finding a new way to represent functions, like as infinite series, can reveal deep connections between things that didn't seem related before. So this equation here is a very famous and important equation, and it reveals a deep connection between trigonometric functions, which you think are about things rotating, they kind of oscillate, and then exponential functions, which, as far as you're concerned, are these kind of growing functions. So these two things are intimately connected together, not in the real numbers, but on the complex plane. And one way of understanding that connection comes through representing them as series. I mean, again, you might say, why do we care about this? Being able to find deep connections between things lets you take a problem, for example, about sines and cosines, and rewrite it in terms of complex exponential functions. That often makes it super, super easy to solve something that would be messy to solve otherwise. It's just like in physics. If you choose the wrong frame of reference for solving your problem, it will be very messy, but once you choose the right frame of reference, the algebra just all works out very cleanly. It can be the same thing in mathematics. So I'll see you on Monday, and we'll talk about some specific tests we can use to see whether or not a series or a sequence converge.